Make it your bed. Here you go. Come back here. Oh, I forgot the calculator. Oh, well, I'll use my phone. Do that. Oh. Next. I'm not turning on. Sure. Okay, so when it comes to the home, I'm confused with versions. I don't know it's because it's the way that you talk or something, but like when you're talking about it says here like what mass, so I know it comes like to mass, like grams. That's like how I determine my limiting reactant and my derivative. But whenever it comes to problems like these, like they just have an equation. Is that what I need to know? Like, oh, I need to convert to moles.
You can actually convert it to mass. You wouldn't have to
I get
stop at moles.
confused on where I need to solve because
I personally convert them all to mass. Because if I'm going to do a percent yield, I need actual yield over theoretical yield.
so it depends on like what kind of what actual yield they gave you in the problem.
Right. That's what it would depend on.
Or the actual yield always going to be like grams.
I mean, I've always done it with grams.
Okay. I did not know.
So it depends upon what they're asking you for. But if they do a percent yield, a lot of times I'll go ahead and convert it all the way to grams.
Now I'm trying to find their actual yield because what I ended up using was the moles. Oh, because I did the actual over the theoretical. I was confused. My friend helped me with this. I just didn't want. I just wanted to show it from your side.
Yeah. So I would have gone ahead and converted this onto grams, and then I would use the actual over the theoretical.
Okay. Okay. I get.
So I tend to do everything grams, and
Okay.
that way I just do one thing all the time. What are you doing to me? Why are you misbehaving? Oh my goodness, let's cut my face open. That's better. It's that time of the morning. So we are going to go ahead and get started. The very first thing I want to do is just make a couple of quick announcements. There are 2 bonuses. One of them is this Thursday night. It is via Zoom. It is, I think it starts at 7 p.m. And you don't have to worry about doing anything because it's my Zoom, so I will know who attended and for how long. So all you got to do is attend. Now, the neat thing is Casey Thurber is a former graduate of UCA in the chemistry department. He went on to the University of North Texas, where he got his PhD in analytical chemistry. Since then, he has moved up to Honeywell in Kansas City, where he is now a engineering manager over the polymer division. The neat thing about Honeywell is it is a part of the DoD, so the Department of Defense. While he cannot talk about everything he does because it is, there's a lot of secrets and rules about what they can and can't discuss. He is going to specifically talk about his trajectory, especially how the things that he learned as an undergrad have applied even as he went on into grad school and then on into industry. The neat thing about that is it'll give you an idea of some of the skills that you're picking up and how they can apply when you get out into the workforce. And another thing that he is specifically doing is he's not just going to talk about it from a chemistry standpoint, but he's got people that are biology majors that thought they were going to go to med school and then wound up going, they were able to go on into the lab as well. So he can talk about a variety of different things. He will mention some of the stuff that Honeywell does, but it's going to be only a portion of his talk. Most of it's going to be the trajectory from undergrad to grad to life and industry. And then the other one is I posted, I believe it was yesterday, in the bonus folder. You have the opportunity to donate food to the Bear Food Pantry. I will take 10 items, and for every item you donate, you'll get 1 bonus point. So it's based on the number of items. And I gave a list of the things that they particularly like over there. These are things that tend to give the most energy for the longest period of time for those that, and if, by the way, if you are ever, if you or your family has any food insecurities, I don't know how many of you are aware, but we do have the Bear Food Pantry on campus, and any student, staff, or faculty member that is struggling with food insecurity can go over there and get food. I believe it's once every 2 weeks, if I recall. So that's just something that, but I like doing this. And right now the Bear Food Pantry is pretty, the last I heard, it's pretty decimated. So I figured this is a good time for me to do this bonus, which I typically do in my classes, where we can donate some food back to the food pantry. There is no quiz today because you had a test on Thursday. However, I will be posting a homework after class. It's going to be over what we covered today in class. I have not finished grading exam number 3. I am going to be working hard today and tomorrow when I have the opportunity to try to get them all graded, but we will see where I get. Now, that being said, the W deadline for classes, whether it's my class or any other class, is on Wednesday. And I don't know how many people are aware of that. The only reason I'm bringing it up is if you are on the line of, do I stay or do I go? You can come see me and I'll grade your test specifically. But if you're not on that line, I do ask that you be patient with me, but I'm going to try to get them done by Wednesday, or try to get them back to you Thursday morning. But anyhow, we'll see what I can manage. Any questions? The information for today or this week is up on Blackboard. And I think that's all the announcements I had. So, okay, before I get into what I am doing today, I would like you to tell me what all you learned on the Tuesday before the test. Because I want to make sure I don't skip anything. You did what? Where you were calculating the molarity or doing dilution or what? Okay, so you did both of those. Huh? And you did theoretical yield and percent yield, limiting reactant, and what? Excess? Okay. I just wanted to make sure that all of that was covered before I jump in, because I don't want to just jump in and blow your minds. So I had to know what you definitely covered. I figured you covered it all because Dr. DeRocher talks a lot faster than I do typically. So I figured you covered it all, but I wanted to make sure. Any questions from me before I start? Can you believe we only have 3 weeks left? It's scary, but we'll make it. I do want to tell you one thing in this 3 weeks that we have left. So this week it is strictly lectures and the thermochemistry lab. Next week on Tuesday, I will be lecturing. I will be going over redox reactions, I hope by then, and getting started into the thermochemistry a little bit. Then after we get back from Thanksgiving break, we will be focusing our attention in class on the thermochemistry chapter. And I know I have a lab scheduled for the week after Thanksgiving break, and I've decided that I will do the entire gas law lecture, which usually only takes me like an hour and 15 minutes in the lab. So, because I don't go over the entire chapter, I go over the main points and go. So, what that means for the gas law lab is if you attend, you get your 25 points. But there will, but anyhow, I wanted to give you an update on where that's all going. And then I believe it's the Tuesday before study day is our last exam of the semester prior to the final. Any questions? Okay. Then let's get started. So we are going to start with some more molarity problems. Specifically, we're going to get into using molarity as a conversion factor. If you look at the formula for molarity, you're going to see it has moles over liters. In other words, we have two conversion factors. I mean, we have 2 units. And so it makes a very good conversion factor. And so the first type of problem I'm going to do is what I consider to be a fairly straightforward, simple conversion using molarity as the conversion factor. And then the second type of problem I'm going to do is going to combine stoichiometry, which you did with Dr. DeRocher, with molarity. And we'll actually look at it from a perspective of a reaction. Okay, come on, be nice. So let's just look at an example and I'll explain it as I go. So how many moles of H2SO4 are present in 1.63 liters of, where was I? A 0.954 molar solution. So folks, just like I've been doing, I tend to break out everything that I'm given. So I see that I am given a volume. So I'm given 1.63 liters. And I see that I am given a molarity. So that is a 0.954 molar solution. In this particular case, that would be molar H2SO4. I identify what I want to solve for, and what I want to solve for in this case is moles of H2SO4. Now, the question is, which piece of information am I going to begin this calculation with? I got 2 pieces of information. Which piece do I want to start with? To help you identify that, you really need to take this, it takes 1 second, really. You need to take this molarity and go, okay, what is molarity? This capital M says that it is 0.954 moles of H2SO4 per 1 liter of solution. If you take that just couple of seconds and rewrite the molarity in its subunits, then it becomes more obvious where you're going to actually start this calculation. Because way back in the beginning of the semester, I made a comment about if you can start a calculation with a value that has only 1 unit associated with it, that is where you should start. So if that is the case, then I am going to want to take that 1.63 liters, and that is what I'm going to convert into moles of H2SO4. So the 1.63 liters of solution. Now I want to convert that volume into moles. That means I need to use this molarity. I have liters in the numerator. To cancel out the liters, I need the liter portion of the molarity in the denominator. And therefore the mole portion will go into the numerator. We place the liter portion in the denominator so that it would cancel. And we already have what we want to solve for, so it's a matter of keying it into the calculator. So 1.63 times 0.954 gives you an answer of 1.555 moles of H2SO4. That if we are recording this answer to the correct number of significant digits, we would record it as 1.56 moles of H2SO4. Questions? Let's look at one more that's fairly straightforward and simple, and we're going to get one that's a little bit more complicated, and then we'll go on to the stoichiometry. So let's do how many liters of solution are needed to make a 1.66 molar solution containing 2.11 moles of KMNO4. Just like before, I'm going to start by identifying what I was given. I was given that it was a 1.66 molar solution. And I was given the fact that I had 2.11 moles. Of the KMNO4. Now, which piece of the puzzle do I want to start with? Again, anytime I see that capital M, I'm going to break it down into its subunits. This means I have 1.66 moles of KMNO4 to 1 liter of solution. Folks, I see a lot of students that see that capital M and they don't break it down. And because they don't break it down, they assume it's moles instead of MOL. They're going, oh, that's a mole too. It's not the same. You got to break that capital M down because it actually breaks down into 2 subunits. And then I'm going to look at what I'm going to solve for. I'm going to solve for the liters of solution Having broken down my molarity into the subunits, what I need is I want to start with the moles of KMNO4 and convert that into liters of solution. So starting with my 2.11 moles of KMNO4, I want to go from moles of KMNO4 to liters of solution. That means you're going to use your molarity. I have moles of KMNO4 in the numerator. That's what I'm starting with, is moles of KMNO4 in the numerator. That means I need moles of KMNO4 in the denominator. You can take this molarity and flip it over, so that the liter of solution goes in the numerator and the 1.66 moles of KMNO4 go in the denominator. You have to do that in order for the units and the substance to cancel, and you're left with your liters of solution. And when you calculate this out, you will get 1.27 liters of solution. So basically, if I dissolve, I have to dissolve the 2.11 moles of KMNO4 into 1.27 liters of solution if I want a 1.66 molar solution. Let's add one step of complication, and then we're going to move on to the next type, which is including stoichiometry. What volume of a 0.88 molar solution can be made using 130 grams of FeCl2? So looking at what I've been given 130 grams of FeCl2. And I have been given that it's a 0.88 molar solution. Now, again, that capital M comes in. I'm going to break it down into its subunits of moles over liters. I also see that I want the volume of that. So I'm going to be converting into volume. And where I'm going to start is I'm going to start with the grams of FeCl2, and I want to convert that into liters of solution. Now, volume of solution. Typically means you need to use the molarity as a conversion factor. But I also notice that I have grams. And just like before, when I have grams, grams means that I'm going to need the molar mass. So I need the molar mass of my iron chloride, iron 2 chloride. Iron has a mass of 55.845. And chlorine has a mass of 35.45. So my iron 2 chloride has a mass of 126.745 grams of FeCl2 is equal to 1 mole of FeCl2. So again, I'm trying to help you take what you're given, folks, and pick apart things. I saw liters, that's volume. So there's a good chance I'm using my molarity. I saw grams, that's mass. So I got to use molar mass. I'm trying to teach you those key things to help you pick things apart. So using this, we have 130 grams of FeCl2 is where we're starting. The very first conversion factor needs grams of FeCl2, so we'll be using our molar mass of FeCl2. We'll put the grams of FeCl2 into the denominator and the mole of FeCl2 in the numerator. That was done so that our unit and our substance, whoops, well, I'll get to that one, would cancel out. Now we need to use our molarity to go from moles to liters. Again, because I have moles of FeCl2 in the numerator currently, I'm going to have to flip my molarity in order to get the moles of FeCl2 to cancel out. So the 0.88 moles of FeCl2 will go into the denominator, and the liter of solution will go into the numerator. It had to be that way so that the unit and the substance would cancel. And now we're ready to calculate. And I come out to get 1.17 liters of solution. Questions about the process? Okay. So just like previously when you were doing stoichiometry, when you did limiting reactants and stuff of that nature, you can use molarity as a conversion factor in a stoichiometric calculation. Trying to find an example of the ones I like. This is a good one. So let's look at an example. Zinc and hydrochloric acid react according to the equation. Zinc solid plus HCl aqueous goes to form zinc chloride aqueous plus hydrogen gas. And we're going to do a couple of different questions related to this. The first one, what volume of 0.1 molar HCl will react with 26 grams of zinc? What is the first step anytime you have a reaction? Make sure it's balanced. In this particular case, to balance this reaction, I am going to need 2 hydrochloric acids. Notice I didn't even pay attention to the problem until I got the question, the reaction balanced. I don't care what you do, that should be your first step, is to make sure the reaction's balanced. If it's not balanced, then balance it. Okay. Now I'm going to pay attention to the question. First thing I'm going to do is list out the information that I was given. I was given 0.1 molar hydrochloric acid. And I was given 26 grams of zinc. I see my capital M, my molarity. First thing I'm going to do is break that down into its subunits. And in so doing, it tells me what I need to start this calculation with. Because if I can, I'm going to start with something that has only 1 unit associated with it. Now, after having done that, I'm going to look back and see, okay, what was I asked to solve for? I want volume. Whoops. Didn't mean to do that. I want volume of HCl. So my goal is to convert this 26 grams of zinc into liters of HCl solution. If it does not specify, you can convert it to liters, you can convert it to milliliters. If there's no specification with respect to volume, it doesn't matter which one you convert to. Okay, so I'm going to do that now that I've got a chemical reaction. I'm going to do the same types of things I've been doing, which is I'm going to look at it. I have zinc, I have hydrochloric acid solution. Because I have 2 different substances, it means I need my mole to mole. So I know that there is 1 mole of zinc to 2 moles of hydrochloric acid. Next, I see grams of zinc. Grams means that I need molar mass. Zinc has a molar mass of 65.38 grams. to 1 mole. The next thing I note is I want liters. Liters frequently mean I want the molarity as a conversion factor. So I will be using that 0.1 mole HCl per 1 liter of solution as a conversion factor. Oops. And yes, I am very color coded. And I don't know if I've ever told you, but you can bring highlighters to a test if it helps. Okay. So now let's do this. 26 grams of zinc. First conversion factor is going to be the molar mass because I got to get rid of grams. So I'm going to put the 65.38 grams of zinc in the denominator with the 1 mole of zinc in the numerator. You place the grams in the denominator so that the unit and the substance will cancel, leaving you moles of zinc. The next conversion factor is going to be my mole to mole ratio. I have 1 mole of zinc for every 2 moles of HCl. The mole of zinc was placed in the denominator so that the unit and the substance would cancel, leaving moles of HCl. My last conversion factor is going to be this molarity, but I got to get rid of moles of HCl, so I've got to flip this thing. So I'm going to put the 0.1 moles of HCl in the denominator with the 1 liter of solution in the numerator. The moles of HCl had to go in the denominator so that they would cancel out, leaving you liters of solution. And now you're ready to perform the calculation. So we have 26 grams divided by 65.38 times 2 divided by 0.1, and that comes out to be 7. Well, actually, if I'm going to do by sig figs, it would be 8.0 liters of solution of HCl solution. Questions? Okay, one more example, and then we're going to move on to the other topic for today, which is electrolytes. Calcium hydroxide reacts with 2 hydrochloric acids to form calcium chloride plus 2 waters. If I combine 15.0 grams of calcium hydroxide with 75.0 milliliters of 0.500 molar HCl, how many grams of calcium chloride can be formed? One thing I notice when I do this is I have 15.0 grams of the calcium hydroxide. And I have 75.0 milliliters of 0.500 molar HCl. In other words, and if I am looking at this, I've been asked for grams of calcium chloride. What type of problem do I have? Well, I'm going to need that. Yes, definitely. I'm going to have to find the limiting reactant because I have both reactants, folks. So this is a limiting reactant problem. Now, when I do a limiting reactant problem, I don't know exactly how Dr. DeRocher printed it or presented it. But when I do a limiting reactant problem, I convert each reactant into the grams of product. And then whichever one gives me the least grams, that's my theoretical yield, and it came from the limiting reactant. So I see that I'm going to have to take and do two problems. In the first problem, I'm going to have to take the 15.0 grams of calcium hydroxide, and I'm going to have to convert that into grams of calcium chloride. That will be my first problem. In the second problem, I see that I have 75.0 milliliters of HCl, and I see that I have 0.500 molar HCl. If I take that molarity and convert it into its subunits of moles over liters, then it shows me which thing I need to convert. And the one I'm going to need to do is I'm going to need to take that 75 milliliters and convert that to grams of calcium chloride. So my two problems that I'm going to have to do are going to be, whoopsies, these two. Okay, so let's begin with problem number one. With problem number one, I see that I have calcium hydroxide and calcium chloride, which means I'm going to need a mole-to-mole ratio. And that mole-to-mole ratio is a 1-to-1 ratio. So 1 mole of calcium hydroxide to 1 mole calcium chloride. The next thing I notice is that I have grams of calcium hydroxide, which means I'm going to need the molar mass of the calcium hydroxide. Calcium has a mass of 40.078. Plus, I have 2 oxygens. Plus, I have 2 hydrogens. Which means I have a mass of 74.092. 7 grams of calcium hydroxide to 1 mole. I also notice that I need grams of calcium chloride. So that means I'm going to need the molar mass of calcium chloride as well. And that will be 40.078 plus that 2 chlorines worth. So I get a mass of 110.978 grams of calcium chloride is 1 mole. So with my first one, I'm starting out with 15 grams of the calcium hydroxide. And I'm going to convert that. I'm going to start with the molar mass of calcium hydroxide. Placing the mass in the denominator. I then will move on to using the mole to mole ratio. To convert the calcium hydroxide into calcium chloride. And then finally, I will use the molar mass of calcium chloride. To get it into mass of calcium chloride. And I get a value of 133.445 grams of calcium chloride. That's only step 1, folks. I still got to do step 2. Step 2 is to convert 75 milliliters of HCl into grams of calcium chloride. Breaking this down, again, what I notice is that I have 2 different substances. So I am going to need the mole to mole ratio. Yes. Did I might have screwed it up. I wouldn't doubt. I don't have my usual calculator here. You're right. It's a huge difference. I don't know what I keyed in the first time. 22.467. Thank you. I hate not having my usual calculator because I can't see what I typed in, but it's okay. Let's see. So I was on the second part dealing with the fact that I had different substances. So that means I'm going to need the mole to mole ratio, which in this case was 2 moles of HCl to 1 mole of calcium chloride. The second thing I noticed is that I had milliliters. Well, because I have volume, it means I'm going to probably use the molarity as a conversion factor. So that's that 0.500. But my molarity is in liters and I was given milliliters. So I'm also going to have to use the fact that 1,000 milliliters is equal to a liter. And then the last thing I notice is again that I have grams. So that means I'm going to need the molar mass of calcium chloride, which I've already done, so I'm not recalculating it. And so I'm ready to begin this calculation. Starting with the 75 milliliters. So I have 75.0 milliliters of the HCl solution. I've got to convert that into liters first. With 1,000 milliliters is 1 liter of solution. Then I can use the molarity, and I can use the molarity as it is given this time because I need to get rid of liters in the denominator, in the numerator. Whoops. So far, everything is canceling out, leaving me my moles of HCl. Now I can use the mole to mole ratio where there was 2 moles of HCl to 1 mole of calcium chloride. That gets rid of the HCl, and I'm left with moles of calcium chloride, which I now need the grams of, which is 110.978 grams. And now we're ready to calculate. And when you calculate this, you get out 2.08 grams of calcium chloride. I'm going to check that since I screwed up the first one. Now I can answer the question that I posed. If I combine the two, how many grams of calcium chloride could be formed? That is when you look at the one that you have the least quantity of between your answers. So I'm comparing this value and this value. The one that I have the least value of is the 2.08 grams of calcium chloride. So this is my theoretical yield. And that means that the HCl had to be the limiting reactant. Questions? Okay. Now we're going to move out of the math associated with the chemical reaction, at least on a temporary basis. And we're going to move into another part of the chemical reaction. So back when we were talking about chemical reactions, it was reactants go to form products. And folks, if I don't remember if I said this to you or not. So when we're starting to talk about a chemical reaction, that is my alphabet. The periodic table is my alphabet. When I combine the elemental symbols, I make compounds, and compounds are my words. When you combine words, you make sentences. And that's what a balanced chemical reaction is it's a sentence. Now, a reaction should tell, now for a chemist, the reaction pretty much has to tell the majority of the story, all in just one sentence. Unlike an English paper where you got to write this monster of a story. We try to tell our story in pretty much one sentence. So, a proper reaction indicates the identity of the reactants, the identity of the products, the state of matter of each of the above, and then there is one more thing that we will indicate. Technically, there's a few more we could, but one more thing we tend to indicate, and that is the energy of a reaction. The majority of what we're going to be talking about in the last 2-3 weeks, whatever I have left with you guys that aren't going forward into Chem 2 with me, we're going to talk about these last two pieces. How do I know what the state of matter is? How do I know the energy of the reaction? How can I predict these pieces of the puzzle? And what exactly does it mean? So that is where we're starting today, is we're going to start with this third piece, which is starting to predict the states of matter of the reactants and products, and actually going from just the formula of the compound and breaking it down and actually looking to see what that compound actually looks like in a reaction. So, to do all of this, the first thing we need to talk about is the term an electrolyte. Electrolytes conduct electricity. To conduct electricity, you need free-floating positive and negative charges. Now, we can actually categorize things a little bit. We can break it down a little bit further. The very first thing is you can categorize something as a strong electrolyte. This is going to be a substance that breaks down entirely into its ions. The next thing we can do, and you might want to leave a space because I'm going to come back and add something behind that. The next thing, give me a break. Back, delete. Skip. The next thing is a weak electrolyte. A weak electrolyte only partially breaks down. into ions. And then we can go in and talk about a non-electrolyte. Which doesn't dissociate to form ions at all. Now, to understand, to take these compounds and actually take them from this broader perspective and really hone in and look like you're looking under a microscope and seeing what these things really look like, you got to know who's going to do what. So, with respect to your strong electrolytes, those compounds will be your soluble ionic compounds and your strong acids. Technically, it includes your strong bases as well, but your strong bases are also soluble ionic compounds. So I don't separate them. I just go with the soluble ionics. Now, here's where here's where some of that stuff I told you way back when comes into play. How do I know if it's an ionic compound? It has a metal. So when I say soluble ionic compounds, I'm looking for a metal. And we'll talk about how to know who's soluble and who's not soluble here in a moment. Now, your weak electrolytes. Your weak electrolytes are your insoluble ionic compounds. When you get to college chemistry 2, you're going to find out that even your insoluble ionic compounds do dissociate just a little bit, but they may not dissociate to any great extent. Included in this category, though, will also be your weak acids and your weak bases. Then your non-electrolytes. Your non-electrolytes tend to be your covalent molecules that are not weak acids or weak bases. Done. Now, there is one more thing I need to include. And while we'll not use it a ton this semester, we'll use it a little bit, but you're going to use it a lot next semester. And that is, we do have a specific arrow notation that we use. When you're dealing with a strong electrolyte, it's going to be, when we write an arrow between the reactants and the products, we're just going to write a normal arrow. Because it means everything dissociates. But when you get to the weak electrolyte, we will use a double half arrow, which means that it sets up equilibrium between the reactants and the products. Okay, so to know who's going to do what, you got to know you got to be able to get to the next piece. Now, I will tell you, I am what I think is nice. I don't make you memorize your solubility rules, but you will need to memorize your strong acids and strong bases. Well, technically, you just need to memorize your strong acids, since your strong bases are soluble ionic compounds. But I don't make you memorize your solubility rules. However, you're going to need to know them and what it all means. Solubility rules. So I'm going to divide this into soluble compounds and insoluble. If I say something is soluble, folks, what that means is that the state of matter will be aqueous. And it'll mean that it dissolves entirely in solution. So that's why it's a strong electrolyte. So we have some soluble and some exceptions. Our first soluble. Look at something. Is going to be anything that contains a group 1 or ammonium ion. Any ionic compound, and that's, I should say, solubility rules are all about ionic compounds. They're not about anybody else. They're about the ionic compounds. Soluble will be anything with a group 1 or ammonium, and there is absolutely no exceptions to that rule. Rule number 1 is very useful. 2, if it contains a acetate, a perchlorate, a nitrate, or a bicarbonate, those will be soluble with no exceptions. Rule number 3 deals with your halogens, your halides. So chloride, bromide, iodide primarily. These are soluble, but there are some exceptions. Those exceptions are when the metal is a silver, a lead 2+, or a mercury 2+. The next rule is your sulfates. Sulfates are soluble, but the exceptions are silver, lead 2+, mercury 2+, and you add calcium, strontium, and barium to that list. Correct. So these would be aqueous, meaning soluble, and the exceptions means that it is insoluble and a solid. Thank you for asking. Now, let's talk about insoluble. Insoluble is a solid. These are going to be your weak electrolytes. Your oxides and hydroxides tend to be insoluble. The exceptions are if they're combined with group 1, ammonium, and calcium, strontium, or barium. And the other ones, for me, there's exceptions to this next rule. I will be honest, there's a lot of little exceptions, but I'm going to just say for this purpose, all other anions tend to be insoluble except when combined with group 1 or ammonium. Now, I want you to take a quick look at these solubility rules. Notice that if you take care of rule number 1, if you take care of rule number 1, I think this thing just went crazy. Not nice. Look at rule number 1, and you will notice that it took care of this statement completely. So in other words, if you do rule number 1, you don't have to worry about the exceptions for those that are typically insoluble because you've already taken care of it. Rule number 1 and rule number 2 are my first 2 go-tos. Then I look for everything else. Another thing I wanted you to notice is I did try to make this easier to memorize, though again, you don't have to totally memorize it in that when we got to the halides, we had silver, lead, and mercury. Same thing with the sulfates, but in the sulfates, we also added calcium, strontium, and barium, just like we did in the first exception. So I always try to make it easy. But folks, rule number 1, rule number 2, do those before anything else. And once you've assigned a state of matter because of rule number 1 and rule number 2, don't even look at those compounds because you're not going to have to worry about it. Because they are the overriding rules. Then what you notice for everybody else, the other thing I want you to note is all these rules are about the anion. So once you've, except for rule number 1. So once you've eliminated rule number 1, everything else is about the anion. And so you look to the anion and then you go, is that an exception or not? So the metal. Okay, so we're going to talk about what all that means a little bit more. I'm going to quickly just talk about your strong acids because I said those were also strong electrolytes. They will also have a state of matter of aqueous. There's 6 of them: HCl, HBr, HI. Notice HF is not. While HF is the most dangerous of the halide acids, it is not a strong acid. It's dangerous for another reason. And then you have nitric acid, perchloric acid, and then sulfuric acid. And if you look back at your solubility rules, you will see all of those things were listed too. But strong bases, they're already stated, but I do want you to know who the strong bases are. They're going to be strong electrolytes. It's going to be group 1 hydroxides. So sodium hydroxide on, calcium hydroxide, barium hydroxide, and strontium hydroxide. In other words, notice that those are the exceptions. To the oxide hydroxide rule. We'll talk about the weak acids and weak bases at the start of class on Thursday. And then we're going to get into the cool part. Well, what I think is cool, which means you need to bring your labs with you, because we will be using your labs and getting into the molecular equations, complete ionic and net ionic equations, and so on and so forth. Huh? Not this Thursday. Y'all just had one. That's the next test will be the Tuesday before study day. Thank you. I see a lot of people didn't get it. Because I saw Jerry. I did not right off see.
That's the thing you were talking about in the beginning.
Tonight.
Is there a Zoom
Thursday.
Thursday at 7?
Mhm.
And then what is the Zoom link?
If you go into your bonus folder in Blackboard, you'll see it, and you just click on, there's a link attached.
Okay, perfect. Thank you.
I did get your emails. I will take that. And then the other thing, at this point, what I'd rather do on the exam is to have you, the material that was covered on exam number 3, when it comes to your final exam, I can go in and pick out that material and add up the grade that you would have gotten on the final and count it for your exam 3.
What do you mean by like count up the stuff that was?
So in other words, I will count all of the final as the final, but then I can take the stuff that was on exam 3 and add up the points, and then make it out of the 125 and count that as your exam 3 grade.
That's fine. I was gonna ask you another question. Is it possible I get a copy of the exam so I can study on it? Or?
Yeah, those are going to be uploaded before the final.
Okay, that's fine.
So I'll be uploading all of them plus the answer key before the final.
That's fine. Sounds good. Thank you, Doctor.
You ready, lady? You ready to go back to the office? Let me shut everything down. Did I not shut that down yet? Not yet.